Welcome to G Fun Facts Online. Today we are dissecting one of the most significant engineering anomalies in the history of aerospace. If you were watching the live feed on October 13, 2024, you witnessed something that defied decades of conventional rocketry wisdom. A 232-foot-tall stainless steel cylinder, the Super Heavy booster, did not splash down in the ocean. It did not deploy legs to land on concrete. Instead, it fell from the edge of space at supersonic speeds, slowed to a hovering roar, and slid gently between two massive mechanical arms on its launch tower. The arms closed, the engines cut, and the rocket hung there, suspended in mid-air. This was the tower catch. It looked like science fiction, but the physics and the economics behind it are rigorously grounded in reality. To understand why SpaceX chose this incredibly risky maneuver, we have to talk about the tyranny of the rocket equation. For the entirety of the space age, rockets were expendable ammunition. The Saturn V, the Soyuz, the Space Shuttle's external tank, they were all discarded. The logic was that gravity is expensive. Every single kilogram of hardware you add to a rocket to help it survive the return trip is a kilogram of payload you cannot take to orbit. Parachutes, heat shields, and landing legs are dead weight for 99% of a mission. They fight gravity all the way up, just to be used for the final 10 seconds of the return. When SpaceX pioneered reusability with the Falcon 9, they accepted this payload penalty. A Falcon 9 carries 4 carbon fiber landing legs, hydraulic pistons to deploy them, and reserves fuel for a landing burn. This works, but it is not optimal for the scale of colonization. Landing legs are heavy. They require structural reinforcement at the base of the rocket fuselage to handle the shock of landing. Furthermore, once a rocket lands on legs, the turnaround time is slow. You have to send a crew to secure it, crane it onto a transporter, manually retract the legs, and truck it back to a hangar. Elon Musk's requirement for Starship is a launch cadence of multiple flights per day. In that operational model, landing legs become a bottleneck. The engineering philosophy adopted here is that the best part is no part. If you delete the legs, you save mass. If you delete the shock absorbers, you save mass. But the rocket still needs to stop. The solution was to offload all that complexity to the only part of the system that does not need to fly, which is the ground infrastructure. This brings us to the anatomy of Mechazilla, the name given to the launch tower at Starbase, Texas. This is not just a scaffold. It is a 469-foot robotic organism. It is designed to withstand the direct blast of 33 Raptor engines at liftoff, and then, 7 minutes later, catch that same booster. The mechanism relies on 2 articulating arms, known colloquially as the chopsticks. These are massive steel box girders, roughly the length of a Boeing 747 wing. They ride on a carriage that travels vertically on the tower, driven by a drawworks system similar to oil rigs. The crucial detail here is how they interact with the rocket. The arms do not grab the booster by squeezing it. If they squeezed, they would crush the thin stainless steel tanks like a soda can. Instead, the Super Heavy booster has 2 load-bearing pins protruding from its side, located just below the grid fins. The chopsticks have a track or cushion on their upper surface. The booster's job is to hover and position itself so those pins are directly above the arms. Then, it cuts the engines, drops, and hangs by its armpits. It is a controlled collision. The rails on the chopsticks are equipped with proprietary shock-absorbing materials, likely a mix of crushable buffers and hydraulic dampeners, to dissipate the residual energy of the landing. Let's get into the physics of the approach, because the flight profile of Super Heavy is fundamentally different from the Falcon 9. After the boost-back burn, the Super Heavy glides back through the atmosphere. Unlike the Falcon 9, which falls somewhat ballistically, the Super Heavy uses its 4 grid fins to generate body lift. It flies at an angle of attack, steering toward the tower. But the most critical aerodynamic distinction happens in the final seconds. The Falcon 9 performs what is called a suicide burn, or a hover slam. Its Merlin engines are so powerful that even one engine at minimum throttle produces more thrust than the empty booster weighs. The Falcon 9 physically cannot hover. It has to time its deceleration perfectly to hit zero velocity exactly as it touches the ground. If it stops too early, it falls back down. If it stops too late, it crashes. Super Heavy is different. It uses 33 Raptor 2 engines. For the landing burn, it ignites the inner ring of 13, then shuts down to just the center 3. These engines have a deep throttle capability. They can throttle down low enough that their combined thrust is less than the weight of the empty booster. This allows Super Heavy to hover. This is the game changer. The ability to hover buys the flight computer time. It allows the booster to come to a halt alongside the tower, translate sideways into the opening between the arms, and stabilize before the catch is attempted. The control logic required for this is staggering. The booster uses a fusion of GPS, inertial measurement units, and likely relative navigation using LiDAR or optical cameras on the tower. It has to contend with the engine kick. In the final seconds, the exhaust from the Raptor engines hits the concrete pad and the base of the tower, creating complex recirculation patterns and acoustic shockwaves that buffet the vehicle. The flight computer is fighting chaotic ground effects while trying to thread a needle with a 20-story building. If the system detects any off-nominal data below a certain altitude, it is programmed to automatically divert and crash into the ocean to save the billion-dollar tower. While catching the booster is a historic achievement, the next frontier is catching the ship, the upper stage. This is an order of magnitude more difficult and has not yet been attempted. The booster stays mostly within the atmosphere, but the ship returns from orbit at Mach 25. One side of the ship is covered in 18,000 fragile ceramic heat shield tiles. This creates a geometry problem. You cannot put lifting pins on the heat shield side, or they will melt during re-entry. You cannot easily put them on the steel side, because the ship lands using a belly flop maneuver and then flips vertical. Engineers speculate that the lifting pins on the ship might be retractable, popping out from behind the tiles only seconds before landing. The risk is incredibly high. If the chopstick arms scrape the side of the ship during a catch, they could shatter the ceramic tiles. If you break the tiles, the ship is no longer safe for rapid relaunch, defeating the purpose of the catch. So why take these risks? Why risk destroying the launch pad? The answer is in the spreadsheets. Removing the landing legs from the Super Heavy booster saves an estimated 10 to 15 tons of dry mass. In rocketry, mass saved on the first stage translates directly to performance. That weight savings allows Starship to carry more fuel or more payload to orbit. When you extrapolate this to a Mars mission, where every kilogram of supplies matters, those 15 tons could mean the difference between a viable colony mission and a failure. But the true economic unlock is rapid turnaround. In the old recovery model, you land on a barge, tow it to port for 3 days, crane it off, transport it, inspect it, and stack it. It takes weeks. In the tower catch model, the booster is caught, rotated, placed back on the launch mount, refueled, and launched again. The goal is to do this in hours. By combining the launch tower and the landing tower into one, SpaceX turns the launch pad into a factory line. The booster never leaves the pad. It eliminates the need for recovery ships, crawler transporters, and separate refurbishment facilities. This success has forced the global aerospace industry to react. China's aerospace sector is moving aggressively to copy this design. A Chinese startup called Cosmoleap has announced plans for a similar chopstick recovery system, and the state-owned contractor CASC has showcased concepts for tether catches, using wires to snag rockets. On the other hand, Blue Origin is taking a different path with the New Glenn rocket. They are sticking to landing legs, but they are landing on a moving ship at sea. They argue this is safer, because it removes the risk of crashing into the launch tower, but they incur the cost of the recovery ship and the transport time. Rocket Lab also experimented with mid-air capture using a helicopter to snag a parachute, but they abandoned it after finding it too difficult to scale. They went back to ocean splashdowns. The tower catch is not just a spectacle. It is a declaration of intent. It signifies a move away from the expedition mindset of spaceflight, where every mission is a unique event, toward an operational mindset. It treats rockets like heavy machinery that pick up and drop off loads without leaving their place of work. The ultimate goal of this technology is Mars. There are no runways or cranes on Mars. While the first landings there will use legs, the long-term vision is to export this infrastructure. The tower catch is the blueprint for building a bridge between worlds. Thank you for listening to this deep dive into the engineering of the catch.